Okay, sorry for the technical difficulties. Apologies. Okay, so last time, before you guys presented your projects, we went through the normalized variable formulation and discussed how we can limit the slopes created by all of these second and third order reconstruction methods. So all methods that rely on a linear reconstruction within the control volume, and somehow for the quick scheme, they create these oscillations because the slopes create new minima and maxima. And we looked at one way to measure monotonicity, which was the normalized variable formulation, phi tilde, and then we went ahead and looked at the convection boundedness criterion, which allowed us to limit these oscillations. Today, we are going to look at an alternative formulation, which in retrospect, I think is a little bit more elegant than the normalized variable diagram. And I'll probably not teach the NVD next year, and we'll just focus on the TVD formulation. So total variation diminishing TVD framework. Okay. Let's first recall our nomenclature and start with the upwind scheme, just for simplicity. And remember, we're after the values of the dependent variable at the faces of a control volume. Once we know the value of the dependent variable, we multiply it by the velocity or use it to compute the flux, and then take the divergence of the flux to build the right-hand side of the hyperbolic equation. Okay? So we're looking at phi underscore f, phi subscript f. And with this nomenclature, C is remember, C is always the upwind value, D is the downwind value, U is the far upwind, and so on. So if the velocities were reversed, this cell would become C, this cell would become U, this cell would become D. Okay, so this is a bulletproof nomenclature. It just works when we're constructing these schemes. But once you go ahead and do an implementation, you can switch to I plus 1, I minus 1 indexing. Okay. But bear in mind now that phi f is the upwind cell donates its value to the phase value, and the slope is 0, right? So there's no reconstruction of a profile for phi inside the cell. It's just the same value all over, so it's a 0 slope, all right? And for a positive velocity, if you take this cell and call it I, at this phase, then phi at this phase, the east phase is phi upwind, and for the west phase is the upwind of the west phase, so that's phi I minus 1, right? And then you can construct your flux. So the right-hand side is negative, the integral of the divergence of the flux, so that gives you flux at the east face minus flux at the west face, all multiplied by a negative sign, and you get this standard finite difference looking formulation for the upwind scheme. And also, if you reverse the velocities, just to make things clear for you, so the east value would become the upwind value, which is this guy, and the west value would become the upwind value, so it would be phi I, and then you construct the flux that way. Okay. That's great. So now, what you want to take from this now is that upwind means phi f is phi upwind. Okay, that's what you have to keep in mind. So now let's look at what's in a second order or higher order scheme. And let's start with the central scheme given by the average value. The phase value is given by the average value of the upwind and downwind values. Okay, so phi at the phase is given by 1 over 2 phi upwind plus phi downwind. Okay. Now, I want to rewrite this in a way to explicitly separate the upwind value and see what's left over. So what's the upwind value in this case? It's phi c. So if we do this, we get phi at the face is equal to phi c, which we know is the upwind value, plus 1 over 2 phi downwind minus phi upwind. Okay? So we know that, from the previous slide, we know that phi f equal phi c is going to give us the upwind value. Okay? But what is this thing here? Phi d minus phi downwind minus phi upwind. Do you have any inclination to say what this is? Is this an advective flux? Is this a dispersive flux? Is this a diffusive flux? Okay, so let's see what it is. So I'm going to take this approximation and assume the velocity is positive for just simplicity. So in this case, if the velocity is positive, the east value is written in this form is phi upwind, which is phi I, plus 1 over 2 phi downwind, phi I plus 1 minus phi I. Okay? So that gives us the east value. And the west value is phi upwind, which is phi I minus 1, right? Plus 1 over 2 phi downwind, which is phi I, minus phi upwind, phi I minus 1. Okay, so I'm putting those values here, and I'm going to put them in the flux, in the total flux, and the net, the integral of the divergence of the flux, to see what this term is going to give us. Okay? So you plug that into the flux, the integral of the flux, you get flux east minus flux west, which with a constant velocity, you get minus c phi east minus phi west. You plug in the values and collect terms, and this is what you get. So what is the first term here? Yeah, that's coming from the upwind, if you remember the previous slide. Now what is the second term? What does this look like? So this is a second derivative, okay? But look at the sign in front of it. It's a negative sign. So this is actually an anti-diffusive flux. So when you look at the central scheme, what is the central scheme doing? It's taking the upwind scheme and combating the diffusion introduced by the upwind scheme, exactly, okay? And so when you do the modified equation, in this case, what do you get? You get a dispersion term. And that's why you start seeing these oscillations, okay, which in the forward Euler case are going to lead to instability, but in a second order scheme, you'll see in a second order in time scheme, you're going to see oscillations, okay? So now the question is this the case for all second order schemes? I'm going to show you that, yes, that's the case for all second order schemes. That I'm going to show you that all second order schemes can be written as the sum of an upwind scheme plus an anti-diffusive flux, okay? So let's look at one other one, second order upwind. It's given by this 3 over 2 phi c minus 1 over 2 phi u. Then you write it as an upwind, phi c, plus 1 over 2 something. Now look, in this case, this is phi c minus phi u. Previously, we had phi d minus phi c, right? So we're changing things, but the point is when you have a difference like this, that is actually an anti-diffusive flux. But in this case, this anti-diffusive flux, it's at I minus 1. It's the second derivative at I minus 1, but it also has a negative diffusion coefficient. Okay? Okay? So this is the case for the second order upwind. Last time we summarized all of these schemes we introduced from quick third order upwind, second order upwind into what we call the K scheme. So let's see if this applies for the K scheme, right? This seems to be a reasonable way to prove that we can write all linearly constructed schemes based on these slopes, generalized by the K scheme. Can we write those as the sum of an upwind and an anti-diffusive flux? Okay, so is this clear so far? Are you with me? That we can write the second order or more rigorously these linearly constructed profiles within the control volumes, we can write them as the sum of an upwind and an anti-diffusive flux. Okay? So let's see how this works for the K scheme. Remember, this is the K scheme. It was weighting an upwind biased slope and a slightly downwinded biased slope, right? So you see this phi d, and then phi upwind and phi far upwind. And it's weighting them by this 1 minus k and 1 plus k over 4. Okay? So now my question is, can I write this in the form upwind, phi c, plus 1 over 2 times something? Okay? And we notice then when we have a difference, so when you see a difference like this in this formulation, this is an anti-diffusive flux and this is an anti-diffusive flux. Okay? So both of these are actually anti-diffusive fluxes. Right, so here's what I'm going to do now. I'm going to take this guy and divide it by phi d minus phi c. Okay? I'm going to take this and divide it by phi d minus phi c. And this is what I get. So phi c, this is the same. And I need the 1 over 2 because I want to be consistent with the central difference scheme. You don't have to do that, but it's the standard way of doing it, okay? And when I divide by phi d minus phi c, I get phi c minus phi u over phi d minus phi c plus 1 plus k over 2 times phi d minus phi c. So we're still equal, right? Okay. Now, I'm going to take this guy and think about it. What is this? It's phi upwind minus phi far upwind over phi downwind minus phi upwind. Okay? Now, if you divide by delta x, the numerator and the denominator, you have phi upwind minus phi far upwind over delta x. What is that? That's a slope, right? And this guy is a slope as well. Okay? So this ratio is what we commonly call the ratio of successive gradients. So if you are at a face f, the ratio of successive gradients of the function, or one way to define a ratio of successive gradients, is this guy, phi upwind minus phi far upwind, over phi downwind minus phi upwind. And we'll show that this is going to be a very important measure, okay? So we're going to call this RF, okay? Why RF? Because this is a phase value, right? So F, this whole thing is evaluated at the face, okay? This is going to have when you program things, you're going to have to think, so if you want to create an array for the ratio of successive gradients, that has to be a flux type array, okay? So we call this ratio of successive gradients, phi upwind minus phi far upwind over phi downwind minus phi upwind, ratio of successive gradients, okay? Now I'm going to take one more step. The difference here between this case and the previous cases is that what you had here was a constant, okay? What you had here was a constant. So what I'm going to do here now, I'm going to call this whole thing psi. I'm going to call it a function psi, okay? So in other words, the generalized linearly constructed schemes using finite volume approach tells us that the value of phi, the dependent variable at the face, is equal to the upwind value, an upwind flux, plus some weight function. This psi is some weight, is a number, right, depending on k and the gradients, okay? That's just some number that is messing with the magnitude of the anti-diffusive flux. Now, before you jump to conclusions and get the aha moment, let's look at what R means, what the ratio of successive gradient means. Now, eventually, you're going to call this psi the limiter function, and you'll understand why. But let's first look at what we mean by this ratio of successive gradients, okay? We have a few situations. The first one is when you have non-monotonic behavior, these functions, R is always negative. So in other words, when the slope changes sign, you are non-monotonic, right? So you're going from positive to negative, you're non-monotonic around F, okay? So F is here. F is right over here, okay? So you're non-monotonic for R negative. When R is equal to 1, you're linear, okay? And when R is between 0 and 1 or greater than 1, you are monotonic, okay? You're monotonic. Now keep this figure in mind, okay? We're going to discuss it a little bit later. R negative, non-monotonic. R between 0 and 1, you're changing slopes. You're still monotonic. R equal 1, no change in slopes. And R greater than 1, there's monotonic behavior and you're changing slopes. Now, in some papers, R is defined as the inverse of this R, okay? That's not a big deal. You can use either one, but don't be confused if you see something in the papers that you can, rather than dividing by phi d minus phi c, you divide by phi c minus phi u. Okay? It's not a big deal. Okay. So now we can write all linearly constructed schemes, or at least the ones that are popular that we know of, using this unified formulation. That's essentially the generalized K-scheme. And by simply changing psi, we can recover different second-order schemes. Okay? So let's see how this works. And one more thing, a diagram now emerges between psi of R, the limiter function, versus R, okay? So depending on the value of psi, we can plot a line on the psi-R, on a psi-R diagram. So what is psi for the upwind scheme? 0, right? So on the psi-R diagram, this is what you get for upwind. Okay. What is psi for the downwind scheme? So remember, for the downwind scheme, phi f is equal phi d, right? So if we set psi equal to 2, what happens? Phi c and minus phi c cancel out, you get phi d. So if psi is equal to 2, regardless of r, if psi is equal to 2, you get the downwind scheme. Look at these two boundaries. Now remember the NVD diagram. Upwind was a straight line, downwind. So this is where we're headed. Okay. What about the central scheme? Central scheme, phi d was equal, psi was equal to 1, right? Look at that. Central scheme is right in the middle between upwind and downwind. That makes sense, right? It's taking an average value of the upwind and the downwind value. Okay, now let's get things a little bit more interesting. For the second order upwind, psi of r is actually equal to r. So that cuts a straight line at 45 degrees. Then for the from scheme, you have 1 plus r over 2, and that cuts through this point, 0.5, but they all go through 1, okay? All second order schemes are going to go through 1. And for the quick scheme, CR is 3 plus R over 4. Okay, that gives you the quick scheme. Okay, that's great. So we didn't learn anything new, except we wrote things in a slightly different way. Okay, and we showed that all of these kind of high order schemes, they kind of move around. They all pass through the point 1. Not much of a big deal. Okay. But now, I want you to think a little bit outside the box, okay? What can we do with this? Forget that psi comes from the K scheme now. Imagine psi is an arbitrary quantity that you can set. What can we do with this? Okay, let me what? C, okay, but how does that help us? How does C help us? So we know that upwind alone preserves monotonicity, and it's really effective when we have non-monotonic behavior, okay? So when you have a sharp gradient. But when we are in regions that are monotonic or linear, we want to go second order. So can we manipulate psi in a way to switch between the upwind and the full central based on monotonicity or lack of which thereof, based, in other words, on R? So that's the question we're asking here. An idea emerges, and the question is, can we choose psi in such a way to control the anti-diffusive flux? Now remember, the anti-diffusive flux kills the dissipation from the upwind, and that results in a dispersion term in the modified equation, which causes all of these oscillations that you see in regions of non-monotonic or sharp gradients. So now, can we manipulate that anti-diffusive flux in a way to make it 0 so that we retain diffusion from upwind, or all the way make it fully capable where we want to go switch to central in linear or kind of nice and smooth areas? So that's the question. So in other words, we want to suppress the anti-diffusive flux in non-monotonic regions or regions of high gradients, or in other words, when R is negative, and we're going to set psi RF equal to 0 there. So you set that to 0, then you recover upwind. And we're going to leave it alone in regions of monotonic behavior. Now, how do we choose this in regions of monotonic behavior? Well, we're going to learn how to do that. Okay. So yes, we can do that. But first, we want to make sure we choose psi in such a way that we do not mess with monotonicity. So you can just arbitrarily assign values to psi, right? So we have to follow some guideline. And one way, one can ask the question, so how can we make sure that we choose psi in a way to preserve monotonicity? Are you all on board with me now? Okay. Well, all you have to do is look at the TV. Okay, and this is the TV. Okay, so what's the TV? The TV is a mathematical property called the total variation. And it essentially measures how much change there is in a function. So you don't have to worry about that, but for rigorous presentation of the material, we have to define what the total variation is. And it's essentially the sum. So if you are on a grid, you have values going from 0 to n, or 1 to n. The total variation for phi is defined as the sum of the difference between phi I plus 1 minus phi I over all the partitions, or over all the grid points. Okay? So that defines how much of a change overall, like an integrated quantity of the change of phi on the grid. Okay, continuously is the integral of the absolute value d phi dx. Okay, dx. Okay. Now, we claim that to preserve monotonicity, we claim that maintaining the total variation or decreasing it preserves monotonicity. Okay? So we introduce the concept of the total variation diminishing scheme, a TVD scheme, which essentially preserves or diminishes monotonicity. So we diminishes or preserves or diminishes the total variation. So we claim that if a scheme diminishes the total variation, so the total variation of phi at n plus 1 is less than or equal to the total variation of phi at t, we claim that, and that's actually been proven, that when we satisfy this property, we actually preserve monotonicity. Okay? So that's all you have to worry about. In other words, paper by Hart in 1983, he proved this. He said that he showed that a scheme that preserves monotonicity is total variation diminishing, and a total variation diminishing scheme, so it's a necessary and sufficient condition, and a total variation diminishing scheme preserves monotonicity. Okay? So that's what we want. So we want schemes that preserve monotonicity. In other words, we have to make sure that they are total variation diminishing. That's easier to prove for us. Okay? Because we don't have a tangible touch on monotonicity, but we can use kind of the definition of the TVD. So if we can develop a scheme that preserves this property, then we make sure that it's going to preserve monotonicity. And again, without boring you with the math, maybe we can do this as a homework problem. It's pretty easy. It's pretty easy actually to prove. We can show that for schemes of this form, upwind plus 1 over 2 times psi times phi downwind minus phi upwind, this scheme is TVD if and only if psi of r is less than 2, regardless of r, and psi of r is less than 2r. So if you draw the line 2r and draw the line 2, okay, we want to make sure that psi is less than those. And one more thing, when r is negative, less than or equal to 0, we switch to upwind, essentially. If you satisfy these three conditions, this scheme shown above is total variation diminishing. And we know that if a scheme is total variation diminishing, then it's going to preserve monotonicity. That's what we want. Okay? Now, in compact form, you'll typically see this written this way. For r greater than or equal to 0, psi is the minimum of 2 and 2r. So 2r is a line like this, and then 2 is this line, so we want that region below. And for r negative, we want to go to 0. So let's draw this on a diagram. Okay, so this is psi of r versus r. And the line 2 is drawn up there. And the line 2r is drawn here. Remember, this is upwind and this is downwind. And this is our TVD region. So if you choose psi anywhere here, and also on this line for r negative. So if you go r negative, you just pick this line. But if r is positive, you can pick psi anywhere in this region. That is going to preserve monotonicity. Okay? So we call that the TVD. If you go on Wikipedia, you see these diagrams. That's all that is. That's the region where schemes of this form, phi f is phi upwind plus 1 over 2 psi times phi downwind minus phi upwind. That scheme is going to preserve monotonicity if you pick psi anywhere in this region. Okay? But that's not enough. Because if you choose psi randomly in this region, you may not recover second order in regions where the solution is smooth. Okay? So we not only want TVD, we want TVD, but we also want to preserve at least second order accuracy, okay, in smooth regions. All right. So in R over here, R everywhere, it's reasonably monotonic, especially here for small r. For large R, you may have a sharp gradient, but you're still monotonic. Okay. So how do we do this? Again, it was shown that any high-order scheme, linearly constructed second-order scheme, or the K schemes in general, they can be written as something between the central difference scheme, where C is equal to 1, okay, and the second-order upwind. So remember, the second-order upwind, C was equal to R. Okay. So now to guarantee second order, where do you want to be? You want to be between second order up. You want to be within the TVD and between central and second order upwind. And now emerges the famous diagram that you see on Wikipedia and in other papers. This is it. We're just trying to fish for the region where we pick C in such a way that we get total variation diminishing, which means monotonicity preserving, and second order. Okay? If you don't want to be second order, you have the entire plane to pick from, okay, up to 2. But if you want to be second order, you want to be in this yellow region, okay? And that's the second order TVD region. That's the yellow region, okay? So we started with looking at the second order schemes and the K scheme. We wrote that as the sum of a diffusive flux, or as the sum as an upwind, which is the leading error is a diffusive flux, plus an anti-diffusive flux. And if you leave things untouched, the anti-diffusive flux is going to destroy that diffusive flux, or leave some of it, but it's going to leave a significant dispersion error in the modified equation, which is going to cause oscillations, okay? And then we said, how about we throttle this anti-diffusive flux so that, remember, anti-diffusive flux is actually going to give us higher order, right? But it's also going to give us dispersion. So why not kill it when we are in regions where dispersion is a big deal? So like sharp gradients. Remember, with sharp gradients, a signal is written as a ton of Fourier series, a ton of Fourier modes. So those are going to disperse very quickly. But when you are in linear regions or kind of nicely monotonic regions, you can use central and you'll be okay. You're not going to develop a lot of oscillations. And if you do, C is going to switch to upwind, right? So anywhere your scheme tries to introduce a non-monotonic value, your scheme is going to suppress it, okay? So that's the beauty of this, okay? All right, so let's look at a couple of schemes. We start with the min mod, and the min mod is given by, you will see that many schemes using the TVD framework, they're given by max and mins and a bunch of those things because they're all just kind of lines in the plane. So they're pretty interesting, but rather than doing a piecewise, linear piecewise construction like we did with the normalized variable formulation, these are much more compact and they're much easier to implement. So the min mod actually takes the lower boundary of the second order TVD region. We have to pass all of the TVD schemes, they start from here, 0, and they hit the point 0. And then, you know, they're somewhere in this region, but they have to go through point 1, okay? If you want to be second order. If you don't go through 1, you're not going to be second order. So this guy picks the lower boundary. So this is, remember, this is second order upwind, and then it goes central, okay? Now this scheme is going to be very diffusive, because once we go central, we know we're going to start developing some dispersion. So C is going to switch immediately to this point, okay? So let me show you a simulation of the min mod case. It's pretty dissipative, but it's much better than upwind, because upwind, if you, I wish I put the simulation, upwind is going to be here at this point. You're going to have two like Gaussian curves. But it did a lot of diffusion near the non-monotonic regions, and where you have non-monotonic behavior and sharp gradients, but over here it kind of kept things untouched. Okay? Who heard of Super B? Bumblebee. Did you see the Bumblebee movie, the new one? Okay, you should see it. It's pretty cool. They go back to the original Transformers shapes and whatever first generation. Anyway, Super B is given by this max of 0, min, min. Anyway, what it looks like on this diagram is this line. It takes the upper boundary. So min mod takes the lower boundary. Super B takes the upper boundary. So Super B is going to be quite downwinded, okay, in regions of high gradients, okay? So it's going to skew things quite a bit, all right? So this is what happens with Super B. And it actually generates, in smooth regions, it can start generating sharp gradients like what you see over here, okay? Although this is smooth, it started generating a sharp gradient. So if you apply this on a sine function, you're going to see it steepen a little bit, okay? Or in 2D, it's going to turn into little squares, okay? Another one that I really like, it's the muscle scheme, is given by this nasty expression, but it's easier to describe on the diagram, okay? It's kind of nice. Initially starts at the boundary 2R and then switches. I think this was the from scheme. It hits 0.5, so it takes on the value of the from scheme and then switches back to 2 at R equals 3, okay? It's pretty robust and very accurate. So they're all run to 1 second over here. So that's the muscle scheme, okay? And many, many more. In fact, in your homework, you are going to design a flux limiter, okay? And this is one paper that unifies all of these approaches, essentially based on the same thing, but gives you some guidelines on how you design flux limiters. So now, I want to survey you very quickly. Who's heard of flux limiters before this class? Raise your, yeah, you've heard of flux limiters in the past, okay? Have you used flux limiters in the past? No? No? You have. Did you understand flux limiters in the past? The application, the concept, but okay. Do you understand flux limiters today? Why and how and all these crazy diagrams you see on the internet? I hope that they're just a piece of cake for you now. You look at the diagram, oh yeah, you know, we're going to be in this region. If you forget, come back to these slides, okay? And that's it. That's it for hyperbolic conservation laws. Okay, but before I leave this topic, I'm going to talk to multidimensional advection and your homework. So in your homework, you looked at the distortion caused by using the forward in time, upwind in space a scheme for a two-dimensional linear advection case, okay? And you all got that correctly, and you see kind of how when we move in this direction, you see kind of a bulge forming in the kind of XY in the perpendicular direction. And so that's quite disconcerting, okay? And in your analysis, you went ahead and I asked you to do the modified equation, and you did the modified equation, and you got the first few terms of the modified equation. You had, you know, the original advection terms. You had diffusion in x, diffusion in y, but you also had diffusion in xy, and we call this the anisotropic term. And if you carry out the analysis, if you rotate, like I asked you to do, you rotate your reference frame, you can actually this term disappears, but then you shows you why you get this diffusion in the y prime direction. Okay, this term is called non-isotropic term. Some people call it anisotropic term. It causes kind of this this bulging. So how can we fix this? Well, let's split advection. So what we do in this scheme is a very simple idea. Okay, you first advect in the x direction, and then you advect in the y direction using the values from the x direction, and then this is what you get. So when you do this, what you've effectively done is artificially added a negative d phi dx dy term to cancel that anisotropic term. Okay. And if you do the modified equation in this case, this is what you get. You've effectively eliminated the phi xy term. Okay. It's a pretty simple remedy. And this is a great example for why we do one-dimensional problems. If you know how to do advection in 1D, you can do it in 3D correctly. So if you know how to apply limiters in 1D, you'll know how to apply limiters in 3D. Okay? All you have to do is follow this. So if you can do a split advection scheme, do it this way. Okay? This is going to eliminate all sorts of distortion. Advect in each direction at a time. Okay, and then you can apply limiters in the respective directions, and you'll be fine. Okay. And before I leave the topic of hyperbolic conservation laws, I'll just summarize some of the things that we learned. So in general, you don't have to use limiters. So when you see an incompressible Navier-Stokes solver, we use a central scheme in general for the advective terms. Why? Because we have diffusion present. Okay, so we're not too worried about the advective terms causing, the central scheme causing dispersion. It's in the limit of very large Reynolds number where you start seeing these oscillations. Okay, so then you may want to use limiters, but you can use something better at large Reynolds numbers, or not better, you can use something different, and that's turbulence models, which will effectively add diffusion, okay? So that's equivalent to using a central scheme and artificial dissipation, except that the dissipation in turbulence is actually a model for how turbulence behaves, okay? Now, the development of the effort in developing flux limiters almost exclusively focused on compressible high-speed flows, specifically for the Euler equations. So Euler equations are inviscid compressible flow equations, okay? Where they have a propensity to develop shocks, and you want to maintain those shocks and resolve them. So yeah, by all means, when you go in that direction, yes, your bread and butter are going to be flux limiters. You can use flux limiters with the step 1, that's fine. If you want to preserve kind of structures and advect them, if you're concerned about vortical structures being detached from a helicopter or a fuselage, yeah, by all means do flux limiters and try to preserve all of these vortical structures, right? Okay. To this day, there's people still working on this stuff. It was a revolutionary idea. It's like the equivalent of, quantum mechanics in CFD, getting over the Godunov order value. It's brilliant. Now in retrospect, we analyze it in this nice way. Oh, you write it as an upwind and anti-diffusive flux. It's so obvious. Well, it wasn't obvious at the time. Okay, even the nomenclature wasn't obvious. Okay. And finally, a note of accuracy. What we've done here is actually called slope limiters, not flux limiters. Because what we've done, we've limited the value of the dependent variable, phi f, and then we multiplied it by velocity or something else to compute the flux. So we limited the variable, not the flux. So technically, we are doing slope limiters. Okay? You can apply the same idea to the flux. So you advance the variables, and then you limit the flux. It's a little bit different, but they're almost equivalent. I always use slope limiters because they're just easier to implement and deal with. Okay? With flux limiters, you want to limit in time, okay? Because you don't have the value, upwind value of the flux. You don't use that. The flux, you already have the value at the face. And you're computing the flux at the face. What are you going to limit the flux? You're going to limit the flux over time, okay? Because in the finite volume formulation, that integral of df by dx there's also a time integral there, from n to n plus 1. So that's where you limit the flux. It's a little bit different, but but they're equivalent in a way, okay? They'll produce the same results. And I found this link yesterday. It's by Philip Rowe, one of the greatest aerodynamics and hyperbolic conservation law contributor in CFD. It's about an hour lecture on CFD and historical perspective. I recommend you look at it. With that, we'll finish the hyperbolic conservation law lectures. And let's go ahead and continue our coding. We were doing the K-schemes, right? And now we're going to go ahead and do the total variation diminishing formulation. I'm not going to do the NVD formulation. It's the same thing. It's a little bit more complicated to implement. In retrospect, we'll just do the TVD. In the future, I'll only teach the TVD formulation. So let's go ahead and show you how we can implement these flux limiters in practice. And I'm hoping Jupyter Notebook is installed. It's not installed. Okay, so Anaconda. Let me see. I do have the Anaconda Navigator. So I'll open the Jupyter from Anaconda, maybe. Yeah. Yeah. Well, okay, Jupyter Notebook. All right, good. So let me download the couple of notebooks. Okay, perfect. So let me get the K-scheme that we had. The K-scheme in class. I hope you still have some of your notes. So this is what we did in class last week. Okay, can you see? Yes, this is what we were doing in class last week. So actually, we finished it, right? I think we finished it. So let me run it again. Cells, run all. Yeah, so we had a crappy animation done, but that's fine. Okay, so yeah, so if we run it for L over C, the last value should be identical to the first value. So what I'm going to do, I'm going to plot plt.plot sol 0, and then plt.plot sol -1. And that should give us essentially what happened when the signal moves by does one residence time, goes through the domain once. Okay, so you should have this code. We did the periodic conditions. Everything was set up. So all we have to do now is define this ratio of successive gradients, define PC, and then have at it and see what happens. Okay. Pun intended. Okay. So yes, these steps. Do you have your notebooks open? Okay. You have all this code typed up. If you remember, we did the periodic PCs, and then we defined the phi upwind, phi far upwind, phi downwind. Once you have this nomenclature, it's pretty easy. Okay. Do you have any question on? No? Elizabeth, you got that? Okay. Okay, can you produce this plot? Okay, yeah, I still have to post it on the website. Okay, so now let's look at the TVD formulation. So everything remains the same. Okay, you don't change a thing. Okay, you do not change a thing. Now all we have to do is define the ratio of successive gradients. Okay. So remember, our scheme here is we need to go high order in time to remain stable. So in the predictor, we're going to take a half step and do upwind. Don't worry about upwinding in that step. We always do upwind in the half step. But it's in the corrector that we're going to do the limiter. Okay? So if you remember, this is the predictor. So and it's just an upwind scheme. And we do the predictor, flux east minus flux west. So we sorted through the numbers last time. We don't have to go through them again. And we apply periodic BCs on the predictor. Now we define the phi upwind, downwind, etc. Now this was the K scheme. Now this is where we're going to define our ratio of successive gradients. Compute R, ratio of successive. Turn this one's easier for me to see. Ratio of successive gradients. So every time you have a ratio, you're going to have to worry about 0 in the denominator. Okay? So here's what we're going to do. There are several ways to deal with this. You can just simply take the ratio and add 10 to the minus 6 in the denominator, you know. And then if the numerator is 0, you're 0. And if the denominator is 0, then you're going to get something order 10 to the minus 6. But we don't care. For large R, we're capping C at 2. So we don't worry about these extreme values for R, whether they're negative, very large negative values, or very large positive values, because we're capping the limiter function to 0 and 2. Okay? So don't worry about that. You can do it numerator over denominator plus an epsilon. But there's a slightly nicer way to do this. And we're going to do the numerator, or numerator, or top numerator. Let's call it numerator. And that's phi C minus phi U, right? So if you remember, let me get the slides. So if you remember, R was the ratio of successive gradients. So this was R. Phi C minus phi U over phi D minus phi C. Okay? Now, I'll follow up on the case when the ratio is defined as the inverse of this ratio. Well, it's not going to impact psi because psi is going to be symmetric with respect to 1 over R. Okay? So many flux limiters are symmetric. Okay? So psi R over R is equal to psi of 1 over R. That's the symmetry for psi. So doing 1 over R is not going to be a problem. Okay? But either way works. Okay? So numerator is phi C minus phi upwind. Denominator is phi D, phi downwind, minus phi upwind. Okay? So where is the keynote? Okay? Phi D minus phi upwind. Okay. So now what I'm going to do, I'm going to find all the locations where the denominator is, so I'm going to find the locations where I'm going to do this division. Otherwise, yes, so find all the locations where the denominator is not 0, essentially, or is greater than a certain tolerance. Okay, and we'll do the division there. And otherwise, we set psi to, we set R to whatever value we want, like 1 or something, and then let psi pick that up, okay? So sorry, that took me a minute. Find the location where the denominator, or the absolute value of the denominator, right, because we don't want to worry about the sign, is greater than, let's say, 1e to the minus 6. Okay, that's a reasonable value. That's where we will do the division. Okay, so divide locations, divide log is, there's a nice thing in NumPy called np.where. So it gives you the indices of where a certain value in an array is satisfied. Okay, so we're going to say np.where of np.absolute of the denominator is greater than 1e to the minus 6. Okay, So np.absolute denominator is an array. Agreed? np.absolute of denominator is an array of absolute values of the denominator. We're just finding where the indices, where the locations where the denominator is greater than 10 to the minus 6. In other words, it's not 0. Okay? So that's what we're looking at. Okay? And then we define R. Now, define R, set it equal to 1. Okay? R is mp.1s, like we want R to be of the same. Now, R should technically be the same size of the flux, okay? The same size of the flux. But what I'm going to do it here, I think it's not going to matter if I do it equal to phi c. So mp.1s is equal to phi c, okay? And then what do? We say R at divide locations. So those are the locations where the denominator is not 0. That's simply numerator at the divide location over denominator at the divide location. Or you can do R is equal numerator over denominator plus 1e to the minus 6. Okay? You can do that. Okay? Because if the denominator is 0, it's going to give you a nan. It's not going to compute. No. This is an alternative way. Or you can do this. Okay? Yeah, it's another way. Okay. Now compute the phase values. Okay. So now compute the phase values. Okay. Phi f is equal to mp dot zeros like phi c. Okay. Let's see. Okay. So let's start with the min-mod scheme. So first we declare the phase value variables. Okay. Now let's do the min-mod. Okay. And all you have to do is define psi. Okay, because everything else, so psi is only a function of R, but everything else is just essentially weighting the upwind and the downwind and upwind values. Okay, so psi in this case is mp dot maximum. You can't use mp dot max or mp dot min because this is an array operation. Okay, so you wanted array pointwise comparisons. Okay, if you use mp dot max, it's going to give you one value across the array. What we want here is comparing different arrays with each other, 0 and 2R and 1 and etc. So if you look at the min-mod scheme, this is a np.maximum of between 0 and the minimum between 1 and R, but this needs to be an array of values, okay? So don't use np.min, np.max, np.maximum of 0.0 and np.minimum 1 and R. And this will guarantee you an array, okay, of the same size as R, okay? And that's it. That's min-mod, okay? So now compute the val. Okay, so let me move this guy here. Compute the phase value. Phi f is mp.zeros like. Phi f is going to be equal to phi, c plus 0.5 times c, right, times phi d minus phi c, right? So that was our scheme, our general form, that phi f is phi upwind plus 1 over 2 times psi, phi downwind minus phi upwind. That's all you have to do. Now for the flux, it's essentially just phi f, okay? Phi f, right? Or c times phi f. But what I'm doing here is setting the values on the interior faces and then multiplying C by the flux to make sure everything outside is 0. It's just a silly way of doing it, but that's it. Okay, so let's see what happens. Let's run this again. Okay, look at that. How do you add? Once you have this set up, the sky is the limit. You can just, all you have to do is define. So let's do super B. Okay, super B is a little interesting. C is MP dot, so let's see what super B is. Okay, super B is max 0 min to R1 and min R2. Okay, so MP dot maximum 0.0 and MP dot minimum. You can define MP dot minimum as capital min, okay, like declare it to simplify things, but I'm not worried about optimizing your programming now. Just worried about getting it done. Okay, MP dot minimum of 1 and 2 times R, and MP dot minimum of 2 and R. Correct? Okay, let's see. Yeah, max of min 1, 2R, and 2R. Okay, that's super B. So we noticed that in my simulation, super B was slightly biased to the downwind. Okay, awesome. Right? What about muscle? Muscle. C is, this one is a little bit more complicated because for some reason, I couldn't do the minimum of 2R and 1 over 2R plus 1 and 2, right, to separate it into multiple minima. So let me actually try to do it this way. Let me try to do it. So it's MP dot maximum of 0.0 and, how is it? MP dot minimum 2R, 1 over 2R plus 1 and 2. Minimum of 2.0 times R and 0.5 times R plus 1 and 2.0. Okay. When I did this the other day, it threw an error. Yeah, 2R. Okay, so for some reason it doesn't do the minimum this way. So although it allows me to do 3 values in the maximum, it doesn't allow me to do 3 values in the minimum. So what I'm going to do, I'm going to do 2 minimums and MP dot minimum. Okay, you see what I did? I did 2 minimums. Okay, and now look at the beautiful muscle scheme. Flux limiters. So how would you do this when you have different velocities? Yeah, you can do MP.where, or you probably want to go to a C++ code or a for loop based structure. You check you loop over the faces, you check the velocity direction at the face, you pick your upwind, downwind values accordingly, you compute psi, and you move on. Okay, if you want to do it vectorized, if you just have a constant velocity, all you have to do here is put an if statement. If C is positive, this is the upwind, downwind, and far upwind. If otherwise, you put the correct indices, but everything, remember we use this nomenclature to avoid I and ij and I plus 1, I minus 1 indexing. So think of it as upwind, far upwind, downwind. Okay, so change those arrays based on the direction of the velocity, and then you're good to go. So that's the only region where you change, and you'd also want to change the predictor as well because you're going to be backward difference. Okay? Do you have any questions? That's really it. You know, there's nothing more to these flux limiters. There's a lot of literature, arguing about the order of accuracy for these schemes. Are you really truly second order, or are you first order? Since we're combining upwind and second order, we're probably gonna, the first order error is gonna probably dominate unless, you're limiting that first order error to a few points in the domain. How is that gonna behave as you converge your solution? So those are all interesting questions to look at. But qualitatively and quantitatively, we were essentially able to suppress these oscillations in a very intelligent way and surpass a very important mathematical theorem, the Godunov barrier, but for linear schemes. So these are nonlinear schemes, right? Your psi is changing randomly, and you can actually plot. So let's plot psi on top of these guys. So plt dot plot psi. Okay. So let's see what this means. We said that for psi between, so if psi is capped at 2, we're switching to downwind, okay? So you see, in this case, well, this is psi for the last step over here, right? So you see here, psi is nearly going to 0, closer to upwinding, nearly going to 0, closer to upwind and this gradient, and it's going up to 2 in these regions, so it's going to pick the downwind case. Now remember, psi is RF. It's shifted to the faces, so you got to shift this by like half a point, okay? And here in this non-monotonic region, we're going to go between 2 and 0, okay? So we're going to upwind and downwind accordingly, and that's why you see kind of this thing flatten out. In smooth regions, psi is somewhere in the second order TVD region, okay? So it's where these peaks are, where you're switching to a first order, essentially first order scheme, whether downwind or upwind, okay? But this guarantees you monotonicity, okay? And initially though, so if you take a single or you don't take any step, we can see the initial, or you can save your psi's and see how they change. Let's see. Okay, let's save. Oops. Let's save psi and see how it changes. Psi's, okay. Where is psi? Psi dot append. Okay. So let's run this again. So psi, let's plot 0 psi. Okay. Sorry, psi's. Okay. So this is the initial condition. Okay. Look at, all you want to worry about is, so we're guaranteed that psi is going to be less than 2r, so we're not worried about that. What I want to look at are the bounds, where psi is going to go to 0 because r is negative. Remember, we're changing sign, so psi is going to go to 0. And otherwise, for large r, that's going to go to 2. So if you look at the muscle scheme, or actually, let's do it for, this is a good exercise. I've actually never done this before. So let's go to the min mod, okay? So min mod, go back to the min mod. Okay. So the min mod is going to pick the lower boundary, okay? Psi is going to be 1 for all r's greater than 1, and it's going to be r, so between 0 and 1, and for r negative is going to be 0. Okay? So where is psi 0 here when r is negative, when we are changing slope? Okay? So at these points over here, when we're changing the slopes, and at this point over here, right, we're changing slope. So now it's interesting kind of where the points lie. They're not like perfectly symmetric, but so you may not be capturing, all the points here, but effectively you are, right? So it's going to go to 0, 0, and it's going to be capped at 1 everywhere where r is either linear, so you don't have a change in slope, like over here, Over here you have a smooth region, so psi is capped at 2. Okay? And you can animate that, so let's go from 0 to -1 and see how that behaves. And it changes a little bit in these regions. Now we're adding more and more diffusion. Okay? So let's look at the super B. So super B took the upper boundary, if you remember. Super B was taking the upper boundary. So it's annoying kind of to track it over here. There's going to be regions where it's 1 and regions where it's 2 and regions where it's 0. Okay? So that's psi for the initial condition. Let's see it. Okay. So for the initial condition, look at that. In the middle of this point over here, it picked a negative value. Well, that's similar to the previous case. But everywhere here, it's picking 1. It's not even reaching 2, because just the gradients, they're not that high. Okay, they're not greater than 1 or whatever value that is. Okay. Anyway, so it's an interesting exercise to look at. You can spend the day arguing and recording about this, but that's how you implement this.